Amplitude modulation is one of my favorite subjects from signals and systems. It takes something that otherwise would be very mathematically mysterious and makes it just simply intuitive. But before we get into how it's done, we first need to review a rule about convolution. Now, we've talked about how to convolve different signals. Say this. With an impulse. And you can think about how this works in a number of different ways. The simplest way is to think about what it does in the time domain. Whatever x of omega transforms to in the time domain, we know that the unit sample just transforms to 1. And we know that convolving in the frequency domain changes into multiplying in the time domain. So this, in the time domain, is just multiplying your signal times 1. So it shouldn't change your signal. In other words, convolving something with an impulse, a centered impulse, just gets you out exactly whatever you put in. Here's your output, and that has to equal your input. You can also use the flip and shift method too. You'd flip this impulse around, it's the same thing, and then you'd start shifting it around. And when you overlay it on your original signal, you'll end up with another impulse, which is scaled by the height of your original signal. So when you integrate that, you'll end up just with your original signal right back again. Now, given this rule about convolution, you should be able to see that if we convolve this arbitrary signal in the time domain, I'll call it x of omega, if we convolve that signal by a shifted impulse, let's shift it over here to 2. What we'll end up with is our original signal also shifted over to be centered at 2. And this would be our output. When we convolve left with middle, we get right. Take a moment, absorb what that means. We can convolve any signal by an impulse that we've shifted somewhere, and what we get out is our original signal that's been shifted over. Let's see how we can use that property to accomplish amplitude modulation. Now, amplitude modulation, it's also called AM, as in AM radio. It solves a number of problems. One of the problems is being able to broadcast sound over the airwaves. Now, we can hear ranges from about 20 to 20 kilohertz. And that makes it difficult to directly plug it into an antenna. Because for maximum efficiency, antennas are typically have a size of about wavelength divided by 4 or larger. And the wavelength, of course, from physics, you know, it's equal to the velocity of the medium divided by its frequency. So if we're talking about speed of light transmission for electromagnetic waves, we're talking about 186,000 miles per second divided by a low frequency of 20 hertz all over 4. So very roughly, that's about 2,500 miles or larger for your antenna. Not something you want to build. What we're saying here is that you could actually transmit your voice without any modulation over an antenna if it was on the order of 2,500 miles long. So how can we push our vocal frequencies, the frequencies that we can hear, up to a completely different and much higher frequency band? Well, it's called AM radio, and the idea behind that is that you've got someone who's speaking, and we'll call that x of t. And we're going to multiply that sound by a cosine of omega naught t. And that omega naught t is going to be pretty darn high. Let's say it's 100 megahertz. And at that frequency, we're looking at antenna wires that are only a couple of feet. And then we put it through the air. And that air, and I'll draw this gap to show that we might be separating this by many tens of miles. And then at a receiver location, we're going to multiply our received signal again by cosine of omega naught t, the same frequency. And then we'll send it through a low-pass filter. and all this is in the receiver, just like all this is in the transmitter. And let's see what we get out at the other end. Well, this is really difficult to see what's happening in the time domain, but watch what happens in the frequency domain. I don't know what someone's voice looks like in the frequency domain. I'll make it the symbol. So here we are in the frequency domain. And instead of multiplying by a cosine, we're going to convolve it. And we know the cosine looks like two impulses spread over here at omega naught at 100 megahertz and over here at minus omega naught. So it's going through the air, and we said just previously that that will duplicate our input signal and move it up to omega naught and minus omega naught, which is exactly what we want to do. Now we've got our signal not at low frequencies, but up at 100 megahertz where we can send and receive it very simply with a small antenna. Now we're going to convolve it using also the transform of a cosine of omega naught. And what do we get at that point? We get this convolved with this. And by superposition, we can analyze it by looking at what it looks like convolved with this first, and then by this second. So let's do this one first. Here we have this duplicating this at minus omega naught. So there'll be one at minus omega naught. We're going to shift this whole thing over by minus omega naught. So 1 will now be at minus 2 omega naught. And this one will be at omega naught, minus omega naught, or 0. Now let's do it for the right one. That will shift everything to the right, so this becomes minus omega naught plus omega naught. So that will be minus omega naught here. There'll be two of those. I'll call that times 2. And then there's the omega naught shifted to the right by omega naught. So we have one off here at plus 2 omega naught. Then we send it through this low-pass filter. And this low-pass filter isolates the centerpiece. And what we have left for our y of omega is just this centerpiece. And that's exactly what we began with. So therefore, our y of t must be equal to our x of t. Now, it's a little loose with scaling factors. We might be off by a scaling factor. Maybe we'll need to amplify our signal at the end. But the point is that it sounds exactly the same as what we started with, to within a scaling factor. So the first interesting point about amplitude modulation is that it lets us take a signal and move it anywhere we want to in the frequency domain, as high frequency as we want to, and then recover it just the same. But wait, there's more. It gets better. We can take that same idea to accomplish frequency multiplexing. And that involves putting multiple signals on the same communication channel at the same time without them interfering. So here's an example. Let's say we have signals x1, x2, and x3. And we're going to multiply each of these signals. These might be voice communication signals. They might be data communication signals. We're going to multiply each of them by a different frequency. I'll call this cosine of omega sub 1t, cosine of omega sub 2t, and so on. And then we'll add them all together. They go through some long telecommunications line after they've been combined. And that combined signal in the end will be multiplied by 3 different frequencies. Each of these will then go through the same low-pass filter. Well, different low-pass filters, but with the same low-frequency cutoff. And what will be regenerated will be the three signals that have not impacted each other in any way, even though they're being sent through the same single wire. So what's going on in the frequency domain when we do this? Let's see, our x1 in the frequency domain looks like this, and our x2, this is the frequency domain, our x2 looks like this, and our x3, say, looks like this. When we multiply by different cosine frequencies, that's like multiplying them by impulses at different spacings. So this might be the frequency of cosine of omega 1, and maybe we've got our omega 2 out here, and our omega 3 is still further out. So now, let's be minus omega 3. So when we add them all together, we have a single signal that has our x1 encoded here, centered at omega 1, our x2 encoded here, centered at plus and minus omega 2, and our x3 encoded here, centered at omega 3. And when we multiply through on the receiving end, these three multiplications will cause a different peak to line up over the zero frequency point. Let's do it for one example. Let's do it for our omega 1 signal. When we convolve this by our omega 1 again, this will be a little bit hard to draw, but we'll get this entire thing moved to the left. So that will look like, and this will be pushed off at minus 2 omega naught. And then this right one will be copied over here. So that's when it's convolved by this left guy. When it's convolved by the right guy, this will look like, this will be doubled. These three are these three, and then these right ones will be pushed off still further. And then when we low pass, we recover our x1. And the same type of operation will occur to recover our x2 and our x3. This is really, as I said before, seems like magic. You can do the work purely in the time domain. But in the time domain, doing it mathematically, you lose this beautiful intuition here about how you multiplex all these signals on the same wire and have them live perfectly peacefully together. And then down here, how that receiver process demodulates the signal to uniquely recover our x1 or our x2 or x3 or any number of these signals up to the bandwidth of your communication channel. A single copper wire can hold many thousands of voice communications at the same time. A fiber optic channel can hold many hundreds of millions of voice communications over the same single fiber optic strand using this technique.